Okay, let's go ahead and pick up where we left off. We're working our way through chapter 15. So senses, we left off at the ear. We're talking about the structure. So we already talked a little bit about some of the microstructures, some of the cells that are in the inner ear that basically are responsible for your ability to hear. And we take a look at the overall ear. It's basically broken into three major sections. You have your outer ear, which is the part that you see on the side of your head. You have your middle ear, which is the part that you don't see because that's behind your eardrum. And then your inner ear, which is also a part that you don't see because that's actually encased inside the temporal bone, which is a skull bone. And so the outer ear, which basically is composed of what's called the pinna, that's the floppy part that you can kind of pierce and do whatever you want to with. And then, of course, the auditory canal, which is essentially the ear canal where the sound goes in. And so in the auditory canal, because it's exposed to the outside world, it has a little bit of protection associated with it. For instance, it has little hairs in there. Sometimes you can kind of feel those. And you do have actually kind of, well, they're sort of like sweat glands. They're not actually sweat glands. They're a little bit different. They actually secrete a very specific type of substance called cerumen. It's earwax, basically. And so these are what's called ceruminous glands. They're a type of modified sweat gland. So you have two major sweat glands, eccrine sweat glands, which is associated with what you associate with your skin when you sweat. And then you have apocrine sweat glands, which are typically located in your armpits, in your genital region. And so those are slightly different. They have a little bit more of a lipidy secretion. And then, of course, you have this particular type of gland, the ceruminous glands, which is secreting a very waxy substance. And so the reason why you do this is simple. You're open to the outside world, and so essentially you're just trying to guard against stuff getting in there, right? Think of it as sort of like flypaper, right? So you're just like all sorts of dust particles and things like that fly around your head. They're getting into your ear, and the idea here is they stick to the cerumen or the earwax, and then that way it doesn't go into your ear itself. If it went into your ear, then it would start compromising the structure and the function of your ear. So that's earwax is actually a good thing, right? So it basically kind of keeps that auditory canal clear of debris and make sure it doesn't get all plugged up. Now the middle ear, which is basically just behind the eardrum, which we refer to as the tympanic membrane. This is a region, it's an open region, a cavernous region. And so there's a couple of different things in there. This is typically there'll be two different walls on either side of the middle ear. On one, you have the tympanic membrane. On the opposite side, you have what's called the oval window. And then just below that is what's called the round window. And so the round window and the oval window are connections to your inner ear. So you can kind of think of the middle ear as sort of like an antrum or like a waiting room, a foyer of sorts, before you get into sort of the inner portion of your ear, which is really where all the important things in terms of hearing and balance and things like that are happening. So in this area, you also have connecting these window systems, especially the oval window and the tympanic membrane, are what's called auditory ossicles. These are small little bones that are going to be found in this area. They're connected together. And the first one that you're going to see is what's called the malleus or the hammer. And the malleus's job is to grab onto the tympanic membrane, and then it will connect and attach to the incus, which is the anvil. And they're called anvil because this is what they look like, right? So the malleus is kind of hammer shaped, and the incus is kind of anvil shaped. And then the incus is sort of like a wedge bone in between the malleus and the stapes, which is called the stirrup because it looks like a stirrup. And this is the one that connects to the oval window. So what you have is actually kind of a multi-jointed system that moves and is designed to move back and forth. And so this is kind of what it looks like. So here's your outer ear in blue. So you can see the pinna. That's basically the ear portion that you associate your auditory canal is the region that you can stick your finger into, and you can kind of touch back here on the tympanic membrane. Now, when you take a look at the auditory ossicles in the middle ear, you can see you start off, first of all, with the hammer, which is attached to the backside of the eardrum. It is going to be grabbing onto the incus, and the incus will grab onto the stirrups. Now, what happens is when the tympanic membrane vibrates back and forth, it basically moves this entire system. This is a movable system. So this will actually rotate, and these ossicles will kind of vibrate back and forth. So they're kind of moving back and forth, kind of like a jointed system, similar to the way that your arm moves, right? So for instance, if I were to take a look at my arm, basically my upper arm would be sort of like the malleus, right? And so that's kind of attached to the tympanic membrane. And then the joint of my lower arm would be jointed with my upper arm. So this would be like the incus, right? So this is connecting to my stirrups, which is basically where my wrist is. So what happens is if I move my body here, then it's able to sort of translate that movement. All of these pieces are moving around those joints so that what happens here can be translated out here. So if I move violently here, it moves violently here. So whatever's happening outside is going to be moving on that through that entire system. And it's going to be moving ultimately that oval window. So on the other side of the middle ear, you can see you have the stirrups, or the stapes is going to be attached to the oval window, which is the entrance point to the middle ear, to the inner ear. And then just below that, you see this little circular structure right there. That's the round window. And the round window basically is the outlet for pressure that's associated with the inner ear. Okay. So what goes into the inner ear has to figure out a way to come out, right? And so the round window is sort of like the exit, if you will. And then, of course, the inner ear is going to be full of the important structures associated with hearing. So you're going to see the big snail, which is the cochlea. That is essentially your hearing organ. And then above it, you're going to see these sort of circular canals, semicircular canals. These are associated with your equilibrium. And then in between these, you'll see you have your cochlear nerve attached to the cochlea, and your vestibular nerve connected to the what's called the vestibules, or the bottom portions of these semicircular canals. Important thing about these semicircular canals is notice the inner ear is entirely encased inside your temporal bone, safe and secure, which is exactly where you want it. Okay. So the auditory tube, which is not the same as the auditory canal, is what's called, what we refer to as the eustachian tube, or if you want to get fancy and impress your friends at a party, call it the pharyngotympanic tube. Of course, if you do that at a party, my guess is you'll probably never be invited to another one. But this is basically going to be connecting your middle ear to your nasopharynx. This is one of the reasons why when you get a really, really bad cold in your nasal cavity, it starts to plug up your eustachian tubes, and then it makes it hard to hear because there's a lot of pressure in there. And so the whole purpose of this eustachian tube is to equalize pressures. So you've got pressure associated with the outside world and pressure associated with the inside of your body. The middle ear is an open area that has air pressure in it. And so in order to equalize the pressure inside your body with the pressure outside your body, you have to have some sort of an outlet. That's what the eustachian tube does. This is basically what happens when you have the popping ear phenomenon when you're going up into the mountains. The pressures outside are changing, but the pressures inside your body are not. And so what happens is that pressure builds and builds and builds, and then eventually you feel the pop, which is essentially your eustachian tube opening up into your nasopharynx and allowing the external pressure to come in and sort of equilibrate. Okay. So, and that's kind of important. That's also what creates a lot of that sort of pressure in the ears, and all sorts of stuff. We need lots of pressure for lots of reasons, not just going up into the mountains, but we can also get it when there's a lot of congestion that can create a lot of pressure as well. Ultimately, the outer ear and the middle ear are air. The inner ear is filled with fluid. And the three main areas that you're going to have are the semicircular canals, the vestibules, which are at the bottom of those canals, and then the cochlea, which is basically your hearing. Now, typically speaking, when you have sound coming through, what's going to happen is sound waves will go through and they'll strike the tympanic membrane and it'll cause it to vibrate. Now, when it vibrates, it's going to be pulling on the malleus, which pulls on the incus, which then pulls on the stapes, and the stapes will be pulling on the oval window. And so the oval window will vibrate with the same frequency as the air that's coming into your ear. So one thing to remember is that when you're oscillating these ossicles, it's kind of like an amplification system. So if I have just a little bit of air coming at you, it's not enough physically to actually cause massive vibration. But what happens is your tympanic membrane and the ossicles are so sensitive to movement that when even just those very slight air waves come at you, it will drastically vibrate the malleus, incus, and stapes, and then that will allow you to be able to hear the sound. Remember one thing. When you're looking at waves, waves by physics are all the same. If you look at the physics of waves, there's no difference between a wave in water and a wave in air. The only difference is the medium, right? So waves will move with the same physics and the same dynamics in air and water, right? Because you're just basically moving stuff. That's all a wave is. You're moving stuff. In one case, you're moving air particles, air molecules. In the other, you're moving fluid molecules. So what happens then when the sound waves, right? Because that's basically all sound is. All sound is compressed air that has different frequencies and different wavelengths to it. And so when I compress the air, then that compressed air coming at you in wavelengths will go into your auditory canal, and it'll basically push up against your eardrum like waves striking the shore. And so as it does that, it's going to move these auditory ossicles, and those auditory ossicles are then ultimately going to move the oval window. Now, here's the thing. What's on the other side of the oval window? It's the entrance to your inner ear. And your inner ear, remember, is full of fluid. So what happens is you're using the airwaves to vibrate your tympanic membrane. That's going to pull and release on your oval window, which basically creates the exact same waves in the fluid of your inner ear that came to your ear in the first place. So you can think of the oval window as sort of like this wave machine, right? Where you're just kind of pushing it back and forth at the same frequency and the same wavelength as the air that came into your ear. Okay, so all you're doing is recapitulating the exact same air wave that came into your ear in a fluid form in your inner ear. Now, the cochlea then has three different types of canals. Now, we're not talking about the semicircular canals. That's a different structure, right? Now we're just talking about the snail, right? The little spiral guy. Inside the cochlea is what's referred to as the spiral organ, or the organ of Corti. And this is kind of where you sense your hearing. And so ultimately, you have a couple of different types of canals. The cochlear canal, which is going to be found inside this organ, is going to be composed of a couple of different things. First of all, there is what's called a basilar membrane, which will typically move up and down. And as it moves up and down, it bends the stereocilia. Remember what we said about the stereocilia? You don't? Because that was last time. Where we said that the stereocilia is this stiff microvilli structure that is mechanically or physically distortable. And that can basically trigger a mechanoreceptor. And so what happens is the basilar membrane, as it moves up and down, bends the stereocilia of these hair cells. And these are lodged in an immovable membrane called the tectorial membrane. So the stereocilia are lodged in an immovable membrane, but they're connected to a movable membrane, the basilar membrane. And so what happens then is once you activate these receptors, these mechanoreceptors, these stereocilia, then they can generate a nerve signal that goes through the cochlear nerve, and then your brain interprets that as sound. This is what it looks like. So we're looking specifically at a cross-section of the cochlea itself. That's basically what this image is down here. First of all, you're going to see three main canals. The upper canal is going to be what's called the vestibular canal. Now remember, these are fluid filled. Now below that is another one called the tympanic canal, which is also fluid filled. And then smashed in between is going to be the cochlear canal, which is also filled with fluid. So it's in this cochlear canal that you have your hair cells arranged, sandwiched in between these two membranes, one of which moves and one of which does not. So if you want to take a look at it, remember your hair cells are basically like little cells with those stiff stereocilia on them. They're connected to one membrane and then founded on another, right? So they're anchored into the tectorial membrane, and those stereocilia hairs are connected to the basilar. So when these two start to move, the tectorial stays put, the basilar moves. When the basilar starts to move, it's going to basically bend those stereocilial hairs, and then that will create your activated reception. So this is kind of what it looks like. This is a blow up of that cochlear region. So here you can see your hair cells, these purplish looking guys. You can see they're connected at the bottom to your cochlear nerve. Those stiff stereocilial hairs are connected to the tectorial membrane on one side, and on the other side there's the basilar membrane. And so what happens is when the basilar membrane moves and distorts, it'll ripple and undulate. It's going to shift and cause these two to move around. So basically the two are going to be moving around relative to each other, and that's going to be causing these stereocilial hairs to bend, and that activates the neuroreceptor. And this is actually what they look like. So here's the actual stereocilia here of the hair cells. That's actually an electron micrograph. Now here's the thing. How do you determine pitch? It's simple, because ultimately your spiral organ, what we just talked about, the snail, is going to be sensitive to different frequencies, and the different frequencies come from the different wavelengths. So for instance, when you have, say for instance, remember frequency is the distance from peak to trough, right? So it's basically associated with wavelength. The idea is frequency is the number of peaks you get per unit space. And so here's the thing. If you get this sort of low, kind of lazy wavelength coming into your ear, then what's going to happen is it's going to create a gentle wave in the fluid in your spiral organ. Now that gentle wave is going to hit the basilar membrane, and the basilar membrane will distort a little bit, right? But not a lot, because it's a gentle wave. And so when it bends those stereocilia, it's just a very slight bend. That activation will then open up these sodium channels, and it'll just let a little bit of that sodium in. So that's kind of a partial activation. It's a gentle activation. We hear that as one pitch. However, if you have another sound coming in that is much, like it's a higher, shorter wavelength, higher frequency, then that's going to be hitting our ears harder, and it's going to be creating a more higher, a shorter wavelength wave. So it's kind of more of an aggressive wave coming through your ear. That's going to really distort and really bend that basilar membrane, which is going to really bend those stereocilia. And then you hear that as a different pitch. So the different frequencies of the waves coming in are the different pitches. And that basically means that the extent to which you bend those stereocilial hairs is what determines your pitch, whether it's a low pitch or a high pitch. So generally speaking, when you have these gentle versus aggressive waves coming in, the longer wavelength tends to be lower in pitch, and they tend to be received by the tip of the spiral organ. This is basically where you respond to lower pitch. And then the bass tends to respond to higher pitches. So there's different regions of the spiral organ that's designed to basically distort for different pitches. And then, of course, those nerve fibers will send that information to the brain so you can actually interpret and understand what the nature of that pitch is. Now, volume is amplitude. Remember, amplitude is the height of the curve. So in a wave, we have wavelength. So a long wavelength is typically low frequency. So this is wavelength. And then amplitude is the height of the curve. So you can have low wavelength, high amplitude coming through, and that's a volume. So the amplitude or the strength of the sound waves is your volume. And so what that happens then is the fluid in the vestibular canal as it's coming through will essentially create more pressure. It's kind of like a giant wave. It's not an aggressive wave. It's like on the ocean. It's like a big swell. You can see the ocean kind of going up. That's a very low wavelength wave, but it's very high volume because you can see, like, most of the ocean rising up. And so what that does, it creates more pressure in that vestibular canal. That's the upper canal, right? And then what happens is that causes that basilar membrane at the bottom of the cochlear canal to vibrate more. And this creates more volume. So the wavelength and frequency is associated with how many peaks are coming per unit second, right? And then the amplitude, how high each peak is your volume. So how far the peaks are apart is your pitch, and how high those peaks are is your volume. Yeah. So if you want to take a look at some different noises, it's always kind of fun because, well, a lot of times you don't realize just how noisy things are. We have a lot of noise pollution, especially in a city. Cities are incredibly noisy places. Obviously, a jet engine, a rock concert, gotta love those, right? You're talking about 125 decibels. So this typically gets beyond the threshold of pain, and you'll start dancing with some hearing loss issues. So remember when I went to U2 concert, which was not open air, it was in what was then Pepsi Center, which is not a good idea to book a group as big as U2 and cram everybody into the Pepsi Center. I literally had my hearing had to recover over a couple of days. It's like I remember going home from that concert, I was talking to my wife on the phone, and I could barely hear her. It sounded like she was whispering, but I had the volume all the way up. That's how bad my hearing had been damaged. But luckily I recovered, and well, I am a little bit more cautious about going to concerts, mostly because I actually like hearing stuff. I would rather hear than not hear. The experience wasn't that great. I mean, it was great. I love the band, but not worth my hearing. Nightclubs, thunderclaps. That's about 120. So you clubbers, right? Those get pretty loud. When you put your earbuds in, this is a common one. We all fall into this one, don't we? You're dancing with danger there, right? It can be, depending on what it is, right? It can be 110, 120. So you could start anywhere you're in that 120 range, you're looking at hearing loss, is what you're looking at. And one of the ways to sort of gauge that is if you're having to torque up your earbuds like beyond its normal limitations to overcome like ambient sound, then that just tells you how loud that is. I've done that every now and then, like when I'm just waiting on the light rail, like at some of those stations, like especially the ones on the I-25 corridor. it's really, really loud at those stations because if you put your earbuds in, you have to torque the volume up just to hear what's going on in your earbuds. On the train too, it can be actually quite loud as well. So it's actually kind of amazing how loud things get. Between the 100 and 200 range, you have things like the chainsaws, the jackhammers. So a lot of these are pretty loud. A symphony orchestra is actually in this range, which is interesting, right? Because those guys aren't plugged in, and yet they're able to create a lot of volume, right? So, of course, here they're saying regular exposure more than 1 minute. Last time I checked, if you're using a chainsaw, you're probably using it for more than a minute, right? A jackhammer, same thing. Notice, however, what a lot of individuals, like workers that are using these regularly do. They're not just out there lollygagging and using a chainsaw or a jackhammer. They've got their ears covered, right? A symphony orchestra. Well, last time I checked, most symphonies written are a little bit longer than a minute. Of course, that's kind of a loaded one, isn't it? Because you have a different experience. If you're the conductor, then you're going to get a different experience than if you're way back in the nosebleeds, right? But that's kind of interesting. Kind of getting a little further down, so 90 to 100, you got things like tractors, the subways, motorcycles, which you can hear all over the neighborhood. Those typically you're looking at a 15-minute cutoff before you're starting to run into danger. The lawnmower is you got about 8 hours now, unless you have like some massive lawn. Typically, lawnmower doesn't require. It's just annoying. It's not damaging because, well, honestly, if it takes you more than 8 hours to mow your lawn, you need to call somebody. Stop trying to do it yourself. But take a look, though. Look at all the people who do lawn management and landscaping for a living. They're not just out there. A lot of them are. They've got their ears covered because they're having to be around that equipment all the time. So for them, it can get over 8 hours. So traffic noise, which is actually pretty loud, it's not really going to hurt you all that much. It's just annoying, right? So that's also tends to be more diffuse, right? Diffuse sound is usually a little bit safer than focused sound, which is one of the reasons why the earbuds are a problem, right? So when you're kind of standing by I-25 waiting for the train and you can't hear, it's not the I-25 noise that's doing the damage because that's diffuse sound. It's you having to turn your earbuds up. What's happening is you're basically focusing the earbuds right on your ear and you're blasting it. That's the problem. It's more focused sound. Okay. So equilibrium. Let's talk equilibrium. So equilibrium is now going to be the other half of this cranial nerve. Remember, this cranial nerve was the vestibulocochlear nerve. We talked a little bit about the activity of the cochlear nerve and how you do the hearing thing. Now let's take a look at equilibrium. This is going to be the split off. So basically when the vestibulocochlear nerve gets to the inner ear, they split into cochlear nerve and vestibular nerve. Vestibular nerve is going to be focused on equilibrium. And where the equilibrium is going to be in your semicircular canals. And then underneath those canals are what's called vestibules. There's two of them. One is called the saccule, which is below the utricle. So you have utricle above, and then the saccule below. And then above the utricle is going to be the entrance to the canal, the semicircular canal. Now, this nerve will basically be taking information from these semicircular canals and sending it to the brain so you can get a sense of equilibrium. And so obviously your eyes are involved there, your proprioceptors and things like that. So let's go ahead and take a look at how these guys work. It's actually kind of cool. First of all, just like with hearing, they're focused on mechanoreceptors. The same kind of an idea. You bend the stereocilia, and that's going to activate the nerve impulse. And so those mechanoreceptors are typically found inside the semicircular canals. Now, the important thing about the semicircular canals is you've got them in the X, the Y, and the Z plane. So that basically means it's in the X, the Y, and the Z. That gives you all three dimensions of space so that you can interpret three-dimensional space. Now, at the base of these semicircular canals is a structure called the ampulla. And inside the ampulla is going to be hair cells, right? We just learned about those hair cells. And attached to them, just like in the inner ear and the cochlea, are going to be stereocilia. Only in this case, the stereocilia are not attached to a membrane. The stereocilia is actually embedded in a structure called the cupula, which is kind of like this blob of gelatinous goo. There. And so ultimately, if you rotate your head in the X plane, the Y plane, or the Z plane, then you will basically move these stereocilia, and your brain will be able to interpret that movement. So ultimately then in the semicircular canals, you have fluid within that semicircular canal. And as you move, that fluid will flow over the cupula, moving it. The cupula will then move the stereocilia. The stereocilial hairs will bend, and then that will generate a signal that goes to the vestibular nerve and to the brain for you to interpret the spatial outputs. And so this is how it works. Here is the ampulla. So the vestibular nerve is going to be connected to these hair cells. So you can see these little hair cells are kind of sticking out. These little stereocilia are these like little whiskers that are sticking out. And they're embedded in the cupula, which is this flame-like gelatinous goo. It's stiff. Now around it is going to be the fluid of the semicircular canals, the endolymph. Now, when you move, and this is like what you see at the base. So here's kind of a view of what's going on there. So this is happening at the base, these ampulla. So when you move, what's going to happen is the fluid, the endolymph inside your semicircular canals is going to slosh, right? Just like if you move anything, a container of water, if you move to the right, the water sloshes to the left, right? So wherever you're going, this fluid is going to slosh. And when it sloshes, basically that fluid flow is going to pass over the cupula, right? That little gelatinous droplet, and it's going to bend that gelatinous droplet to one side. Well, guess what? That gelatinous droplet is also going to bend those cilia, those hairs in the hair cells, and that will then activate a signal that will then be picked up by the vestibular nerve. And since you have these in all three dimensions, you can basically determine rotational motion, right? That's the reason why we said this is rotational equilibrium. So this is like, if you turn your head to the left, what's happening is you're sloshing the fluid in your semicircular canals, and it's bending your cupula, which is bending those stereocilial hairs, and that's igniting that nerve signal to the vestibular nerve. That's the reason why you know that you just rotated your head to the left, because that information went to your brain. Your brain's like, oh, I see, we just rotated our head to the left, right? And so that's basically how that works. Now, what about gravitational equilibrium? This is different than rotational. So what this one does, right, gravitational equilibrium is essentially, it senses your position in the gravitational field. So for instance, if I were to bend over like this, notice I'm not rotating my head, but I know that my head has gravitationally gone to a lower point in the gravitational field. So I have a sense of awareness of where my head is. That gravitational sensation is going to be happening in the vestibules, which are the utricle and the saccule. And so these are like little pouches that are underneath these semicircular canals. They also will contain hair cells who have that stiff stereocilia embedded in them. But in this case, they're a little bit different because what they have also in them is what's called an otolithic membrane. So basically, otolith means auto means ear, right? Like an otolaryngologist. Anybody know who that is? Some of you probably seen an otolaryngologist. We typically refer to them, or we know of them more commonly as an ENT doctor, right? An ear, nose, and throat. So auto is the ear part. Lithic means rock or stone. So otolithic actually means ear rock. And you have a membrane that basically is full of what's called otoliths, ear rocks. These are calcium carbonate granules that basically are settled on this particular membrane. And they're embedded in like the fluid. Now, the reason why you do this is because, well, rocks have gravitational force, don't they? Gravity can act on mass. And so you can feel that mass moving. And so these are sensitive to horizontal movements. So for instance, bending of the head downward, right? So ultimately, what you have is different perceptions. For instance, the utricle will be associated with the bending of the head. The saccule will be involved in more vertical movements. So this one here, going up and down like this, nodding your head, that one would be the vertical movements. That would be your saccule that's doing that. If I tilt my head from side to side, those are horizontal movements. That is my utricle. So oftentimes when you get dizzy, like on a ride or something like that, oftentimes what's happening is you're messing with your otoliths. The reason why you lose your equilibrium, why you get dizzy, is because instead of having a smooth progression moving to the side or up and down, instead you're spinning all over the place. And when you stop, it's like all those otoliths are kind of swirling around, and you're like, wait a minute, am I up? Am I down? Am I up, down, forward, backwards? I mean, you don't know where you are for a little bit, and you're kind of like, whoa, okay, I need to let my otoliths settle down, and then I'm gonna go ahead, I'll be fine. Right? That's what happens when you lose your equilibrium on some of those rides. This is what it looks like. So in the utricle and the saccule, you're going to notice you have your vestibular nerve, which is feeding the hair cell layer. So the hair cells are embedded in this membrane. And so they have their little stereocilia sticking out. Notice it's a very common idea, right? So you have this kind of fluid gelatinous structure, only now you see all these like little granules. So you can see them, they look like little sand granules there. Those are those little ear rocks, those calcium carbonate ear rocks, those otoliths. And if you want to know what calcium carbonate is, basically calcium carbonate is the same thing as chalk. So blackboard chalk is calcium carbonate. Tums, for you Tums lovers, is mostly calcium carbonate. Seashells are calcium carbonate. So this calcium carbonate is in this fluid in your utricle, your saccule. And so what happens is when you tilt, all those otoliths will kind of flow to one side. So here you can see you're tilting forward in this particular case. So we're looking at the saccule. All those otoliths will basically tilt to one side, and it'll basically push and bend all those stereocilial hairs. They'll kind of bend over, and then it'll activate them. And then that'll send information to the vestibular nerve. So if you take a close-up of this, you notice you don't just have stereocilia. In these particular guys, the hair cells have a very specific stereocilia called the kinocilium, which is kind of like the main activator. So whereas the other ones, the stereocilia were sufficient to activate the nerve. In this one, you have a special structure that kind of bends in response to the movement of those otoliths. So in reality, the way that your brain perceives your gravitational position is literally with a bunch of rocks in your head. Basically, otoliths, as they shift and they move to the side with the force of gravity, all my otoliths are now going this way because the gravity is pulling them to this side, and that's bending those stereocilial hairs, and that's sending the message to my brain that I've got my head tilted to the side. Or if I bend forward, all my otoliths now are being pulled forward, and that's telling my brain that I'm bent forward. If I bend backwards, then all those otoliths will get pulled to the side. So basically, I'm just sort of moving them around, and they're sloshing wherever they go, wherever the gravitational force takes them. Whichever way you pitch, that's where those are going to slide, just naturally. And that's how you determine your gravitational position. So if you're at rest, like if your head's just sort of still, then typically these guys are resting on this membrane, this otolithic membrane, and they're just settled above the hair cells. So your brain is like, okay, so we're not moving, right? Then all of a sudden, if you start to move, you're going to get that little slosh effect, right? So it's like, as soon as you move, then you're going to get a little bit of that sloshing because the fluid's going to respond as you move. And then that's going to brush over those hair cells, and that's going to tell your brain, oh, I think we're moving now, because I can feel myself changing my position in three-dimensional space. And so when you displace these guys, then ultimately it'll bend the stereocilia, and then that will be your gravitational perception. So it doesn't just take a single stereocilium to do it. All the stereocilia together will then bend the kinocilium, which is the one that opens up the gate. So this is the one that opens up the nerve impulse. You can think of these stereocilia as having a leader. All the stereocilia are basically saying, you know what? Otoliths are bending on me, they're rolling over me, and they're pushing me forward. But what we do is we basically don't open anything up. So the individual stereocilia don't actually have an activity yet on the nerve impulse. What happens is all of them basically say, you know what? The otoliths are pushing me over. And then what they do is they basically give all that information to their leader, the kinocilium. And then when the kinocilium bends, then that sends the information. Kinocilium basically shows up and says, you know what? I talked to my team, my stereocilia team, and we're all in agreement. The otoliths are pushing us over. So I need to open you up. I need to activate that nerve response. And then that creates that nerve impulse, which then will go to your vestibular nerve so that you can interpret your gravitational position. Okay. That is the end of the semester.